All right, very important reminder. Your lab number 2 has been released. I believe it's due sometime next week. Please check the deadline carefully, and lab number 2 will be very important for your upcoming assessment. I'll mention that maybe later. And for your written test number 1, it's going to happen on Thursday during the class time, right? You already got a PDF guide. And just to be sure, some of you asked me some question. So during the test, no rodent. Okay, you're not supposed to check it. But you might be given some rodent syntax. And then you got to answer some question about it, multiple choice mostly. And also, you might be expected to write in some answer box some rodent syntax. Of course, you wouldn't be able to check it, but that means you should be reasonably familiar with the rodent syntax given what you have done for lab number 1. All right, just to clarify. And if you haven't really done the verification of your 2 accounts, please do so. You really don't want to waste any time on the test day. And just about the review session, it turns out the only time that might work for me will be 7 p.m. tomorrow over Zoom. I wonder if that might work for any one of you. Do you think it might help you guys, maybe? Okay, why don't we do that? And then I'll record a session, and then I'll try to post it hopefully very soon after that. Okay, so you guys can just ask me some last minute question. All right, confirm. I'll do that anyway. Try to show up because even for me to post the recording online, it may have to be already quite late in the evening, so you don't want to wait that late to review. All right, confirm. And I will send you guys some Zoom link today. All right, confirm. 7 p.m. tomorrow. Okay. Alrighty, so for today, we're still going to continue with our bridge controller M0. And of course, today will be the last class before the reading week, since we got your written test number 1 on Thursday. And I think to make up the time for written test 1, I'll give you guys some lecture video to watch. They're very good quality, it's just that you wouldn't have interaction with me. I'll try to limit that to about 1 hour or so it's no extra workload for you. Right? So that's something I can assume maybe when we get started again after the reading week. Okay, so let's now talk about the stuff, right? Let's now recap about the most important syntax we learned from last time was about what a sequence is. And we're going to see something very similar syntactically to a sequence, but semantically they mean something very different, but we'll get there. It's something called inference rule. But just now focus on the sequence. So whenever you got a sequence over here written this way, you got hypotheses, you got the goal, right? And each individual sequence somehow represents some predicate you would like to prove, either true or disprove it to be false, either way. And so that means the truth of it is not necessarily decided when you see the sequence that stands alone. That's very important to remember. And when I introduce the other kind, that's actually very similar to this. I will try to compare them side by side so you wouldn't get any confusion. All right, so that's about a sequence. All right, we got quite a bit of discussion last time. Make sure you review them, and that'll be very beneficial. And this is where we ended with about how to sketch some proof obligation for invariance. Let's just remind ourselves very quickly. And today we need to get 100% formal about it. Okay, let's see. So given this sketch, which we did last time, and that's what we want to prove. We assume, in the antecedents part over here, we assume that all the axioms and also the invariants satisfy the pre-states. That means no prime. Okay, and also, depending on which event we are talking about, think about for every individual event, you should have a sequence like this about invariant preservation. And you have to make sure the guards of the event should be also assumed. That means it is enabled when you take the effects of the event action. And what will be in the goal over here? That will be the invariant should be preserved in the post states. So that'll be the prime version of the invariance. That's what we did last time. Right, so what I'm saying here is still what we learned from last time. But today, we're going to get things formal, okay, just to see how we can do proofs. Before that, there will be one dry slide I have to go over. Later on, we're going to see various kinds of a proof obligation rule. Invariant preservation is one of them. Also, invariant establishment, deadlock freedom, and also something about variance of your system. That's something we'll get into. But they all follow the same formalism that we have to get used to. So this slide here, keep that as a reference point for you. So anytime you see some proof obligation rule, you're not too sure how to interpret that. This will be a slide to look into. All right, so it's a little bit dry, but let's go over that. Let's say we have this model over here so far, right? Remember, we got constants, we got axioms, we got variables, we got invariants, we got events, and also we got some implicit guards, and also we got actions. We got everything we need to really outline some proof obligation. Let's now go over some formal components, like what they really mean. We'll start bullet point by bullet point. Number one would be the list of constants. That one will be easy, okay? So this is something called C. All right? So what we would say is, we're going to say C, for our model, the constant will be a list of constant by definition. It's going to be a list containing just the constant. In this case, the list has size 1. All right? Just 1. That's a constant. That one's easy. You might have 2 constants, you might have 3, but it's a list in general. And we also got A of C. What does that mean? We have some, think about A is more like a function, A, for all the axiom. Given the constant, you can give its definition for the axiom. So you can think about all the axiom will depend on what will be defined in terms of the constant. Okay, let's see how we can do that. So the axiom will be something over here. Okay, so you can think about in our case, we have the set of axiom, and then the constant we know already it's a list of just containing D. So that will be, it will be defined in terms of just the constant D. And in this case, what do we have? In this case, we just give the name of the axiom. That'll be okay, right? So in this case, we just got axiom 0, 1. And again, if you recall, 0 is about model 0. Number 1 here is about the index for the axiom. We might get index axiom 1, axiom 2, and etc. All right, so far so good. And we got 2 kinds of variables. We got V and also V prime. So that's really important, especially we talk about before-after predicates, namely the pre-state value and the post-state value. Okay, let's now do them very quickly. Also here we got the V versus V prime. Okay, each one of them is also a list. So now in our case, the V will just be by definition a list, just n. And what about V prime? Also a single variable, but now be the prime version. Right? Our initial model is pretty simple. You can see the constant only 1, variable only 1. But in general, it could be multiple. That's why it's a list. And just to annotate a little bit more, think about here is the pre-state value. And this one over here with the prime is the post-state value. All right, and let's move on to invariance. And for the invariance, now you can see that invariant usually we just say I, capital I. Invariant can be defined in terms of 2 things, the constant and also the variables, right? It's kind of a straightforward definition. Let's see what the invariants are. For our case, you can see we got invariant here. So let me just circle that. So that's invariant we want to talk about. And C here is the list of constants. And the V here would be the list of variables. Okay? And for our invariants, let's call that I. And that one there is going to be defined in terms of the constant which contains just D, and the variables which contains just N. Right? You can see the definition. D here corresponding to C, and the N here correspond to V. Right? That's the formal definition. And how many invariants do we have? 2. So we're going to do, like in the case of axiom, we're going to just list the label of the invariants. So it would be invariant 0, 1, and also invariant 0, 2, like that. Okay? Hopefully, so far, so good. And I would like to give you one extra notation to also get used to. When you talk about the invariants, you may also have to somehow talk about some specific invariants. Okay? So now, let me show you what I mean. You can see here we got indices for the invariant, 1 and also 2. Okay? You can see here, these are the indices of the invariants. How do we refer to individual invariants? Okay? I'll just give you one example. To really refer to individual invariants, you can say and I give an index 1. It's a subscript. This one is referring to this invariance specifically. Okay? Over here. And then, of course, in general, it could be defined in terms of the constant d and also the variable n. And that one, by definition, is we can just copy that. It will be, for example, n is of that, just like a predicate. Question?
0, 1. Why is it 0, 1? 0, 10.
That's something I just said about 2 minutes ago. Right? So I guess you didn't really catch that. 0 here is about model 0.
Okay.
All right? And the 1 and 2 here are the indices for the invariants. So we have some systematic naming convention here so that we can numerate them. And especially once we get to the refinement level for refinement 1, refinement 2, you have to accumulate all the invariants from the previous model. So having this way to label the invariants systematically will help when you do the proof obligation discharging. Okay, very good. That's awesome. After invariant, we're getting to the end. Guys, don't worry. As I said, the slide pretty dry, but we got to get through it. And the next one. So now we have talked about the global constraint, about constant, axiom, invariant, variables. Let's talk about individual transition, like events. Let's talk about the guard. We use G to stand for guard. And what can the individual events guard be defined in terms of? It can be the constant, and it can also be the variables. It's like a Boolean condition, pretty much like an invariant in some way. All right, let's now write it down. Okay, so let me now try to do this. Let me use maybe this color here. Okay, let's talk about the guard. Okay, so here, let's say in the case of ML out, over here, so you would say for its guard, which can be defined in terms of, again, the constant and also the variable. And in this case, we say that it's implicit, just true. All right, just any Boolean condition. But in this case, it's simply true. It's implicit. Similarly, we can also say the guard for MLN, which can also be, in general, be defined in terms of D and also V. And true. Let me give you a little bit look ahead. Either later today or maybe during the reading week when you watch the lecture video. We will argue very soon that having true guards for our ML, MLN are inappropriate. So we got to fix it. So once we fix it, this guard over here should be fixed accordingly. Right? So this might change as we revise our model. And the next one will be the effects of the event. So that one there is about what's really on the right-hand side value that the variable should really become. Okay, so that will be the effects. So think about this. Let me just use maybe orange. I'm running out of color, but so bear with me. Okay, this will be the effects. All right, effects of events action. All right, how do we talk about it? If you recall, this one here, the action means n prime equals n plus 1. So think about this n plus 1 over here is the effects. We are saying the following. The post-state value of n should become the pre-state value plus 1. So this expression here is the effects by definition. Okay, let's write it down. So what we have is like this. We will say the effects, which can also be defined in terms of the constant and also variable. Okay, so we got a constant d and also variable n. So this can be defined in terms of like a sequence, and n plus 1. Okay, notice one thing here. this is actually a sequence over here. So that means if your event is trying to is trying to change multiple variables at one go, in that case, you may have multiple expressions over here to correspond to their post-state value. All right? So that's why it should be a sequence in general. And not surprisingly, what about this one here? This will be the effects of this event, MLN. So you can think about its effect, the constant, and also the variable will just be n minus 1. You can see here, this effect is defined in terms of the variable. In this case, it just doesn't use the constant d. In general, it could, but just in this case, it happened not to. Final one. Given what we have said so far, we can easily define the before-after predicate. That's the final one to look at. Okay? And we say that whenever you want to refer to the before-after predicate of a particular event, what you gotta say is, it's gonna be the v prime, the list of prime variable in the post states. They should be assigned to the effects of the events. So what do I mean? Let's take a look. That one will be the concluding one, so let's be careful. This will be the before-after predicates. Let's highlight it. Okay, let's take a look. Let's say in the case of the ML out, before-after predicates of ML out. For that one there, first of all, by definition, it's going to be v prime. If v prime, by our earlier discussion, is going to be just the m prime. M prime over here. All right? Should be equal to, this is indeed mathematical equality. It's not assignments in the programming language. And what about the effects of ML out? Effects will be m plus 1. So this will be the before-after predicate. We're saying that m prime equals m plus 1. That's the before-after predicate. And this mechanism here is very general. In theory, you may have more than one variables in your model. That means you may have also more than one effects in your model. So you will just go for the position-wise correspondence for the before-after predicate. Okay? And you will see another example on the slides about before-after predicate for MLN. It will just be m prime, and here will be m minus 1, right? In a similar way. Again, why are we studying this slide that's so dry? It's because later on, when we actually try to define the proof obligation rule for various conditions, deadlock freedom, invariant preservation, you will see symbols like these. So these are the mathematical construct that can make things very precise about exactly how you should formulate constraint. Keep this slide handy and the page, and then whenever you need to go back to really interpret the proof obligation rule, this will be the slide to look at. All right. Question? Adnan? So here, okay, that's a good question. It's not really covered in this page. Let me address that maybe separately. Let me do that. Okay, it was a good question. Very nice question. Event. Yeah, guys, I'll get back to you on this just to make sure. But for the bridge controller example, we happen not to have any event parameters. But I know in your bank example you do for deposit withdrawal. I'll look this up and I'll get back to you. All right, very good. Thank you. Go ahead, please. Oh, you mean this symbol here? Okay, so this is just like a standard symbol for is defined as. Whenever we say something is defined as, so that's the symbol. Yeah, that one, you don't need to worry too much, just a standard one. Okay. All right, let's move on, and let's see what the next one is. All right, so now we were going to actually state formally the proof obligation rule for invariant preservation. But this one here is rather similar to the informal sketch that we did last time. But let's now look at this. And the way to interpret this, in case you forgot how to, this will be the slide to look at what each component really means. But let's take a look at this one together. Okay, so there are various things we need to speak about. Again, you got some model here, and this will be some proof obligation you will have to specify. Okay, and one thing to let you know first, this, even though it's more like a skeleton, like a template, how many proof obligation rules should be instantiated from this has certain factors that we have to consider. That's why I got a question here that we're going to answer together. How many proof obligation rules should be generated based on this for our model 0? More than one, I can tell you, but we'll get there a little bit later. All right, let's now take a quick look again. This part over here is the, let me use a different one. This one here is the axiom. All the axiom. Right, if you remember the A that we did earlier, which will be defined in terms of the constant. And also we got invariance, which is defined in terms of the variable in the pre-states. Invariance in the pre-state. And this one here is the guard of some events under consideration. And the guard itself should also be enabled. It should be evaluated to true in the pre-states. The guard of some event is evaluated true in the pre-state. Right? It's important. You can see the V here is a pre-state. Right? Okay. Good. And let's now move on. And what about this part over here? This one's interesting. Okay. This one, first of all, you can see that's invariant again. This is invariance, but this is II. What's the difference? Okay. This invariant is about all the invariants together. This I here is all the invariants. All the invariance conditions. For example, here you can see we got 2 invariant conditions. So that's why here represent these 2 that we're going to write down in a moment. But this one here is telling you each sequence is only going to handle one invariant condition only. All right? You're not going to try to prove all the invariant conditions in a single sequence. You prove one by one. Okay? So that's why you will see there is an I here, which is about the index. Index of invariance. In our case, we got either 1 or 2. 1 or 2. All right? And then this invariant here is going to be defined as the effects of the events that we're talking about. Okay? Let me write it in this way. Invariance I, right, corresponding to this I over here, should be expressed using the effects of the events, right? All right, let's now see how we can instantiate this particular proof obligation here. But before that, we're going to figure out how many instantiations can we generate from there, right? This guard over here, so let me now try to circle the highlight the ones that's going to represent multiple objects. This is one here. This can be the guard of some events. So let me say star here. Star means it's the guard of some events. And let me put star star over here. The star star over here, specifically I'm referring to the I index over here. Star star. Some invariant condition. The combination out of these two are going to tell us how many proof obligation we will need for this Sequent template. All right? Let's now be systematic. How many guards should we really consider from this model? 2. The guard for ML out and the guard for ML in, depending on how many events you have. Agree? For that one there, it's going to be corresponding to the number of events. All right? And over here, we say some invariant condition, which could be either this one here or this one here, right? So that one, that dimension there, corresponds to the number of invariant conditions. So if we do the math, how many combinations we have for M0? 4. Can you guys see that? Because we got 2 events over here. Each one of them should be shown to preserve the invariant condition, either this one or this one. So that's why we got 2 times 2. All right? So here we got 2 events over here, and we got 2 invariant conditions. So that means overall, we have 2 times 2, which is 4, proof obligations. That's related to invariant preservation. And by the way, this is how Rodin generates proof obligation automatically. For you guys, you should really know how the process goes. Right? All right, that's about just the overall picture. We know that we need 4, but let's now enumerate them together. Okay? And for each one of them, we need some very clear naming of the label for each one of them. Okay? And here is how it will go. I'll give you 2 examples. The other 2 will be left as exercise for you. Okay? Let's try with this. Let's say proof obligation 1, proof obligation 2. Let me try the 2 proof obligation that has to do with ML out. Let's say I try with that. And for the other 2 that are to do with ML in, I'll leave to you as exercise. Okay? How about this one here? This will be the naming convention. First of all, put the event name. You will say ML out. And then slash. The second component will be the invariant condition. Right? That's the I over here. And I can be either 1 or 2. Right? So let's try 1 first. Invariant 0, 1. Okay? And the third component will be about the kind of proof obligation we want to discharge. So here we are talking about invariant preservation. Later on, we got invariant establishment and also deadlock freedom and etc. So that's why here the third component is also important. And for invariant preservation, we just say INV. Okay? Obviously, this will be the event name. This will be the invariance condition. This will be the nature of the proof obligation. Now, how do I write out the other proof obligation that has to do with ML out? That's the question. ML out, still the same events, but now this part here should be different, right? Since now I should be talking about the second invariant condition. So it should be invariance, still model 0, but index 2. And then I'm still talking about invariant preservation. Okay? The exercises for you will be, well, what about proof obligation 3 and 4 that have to do with ML in? I'm pretty sure you guys can work out the naming convention, right? You will see that also on the slides later. I would say PO3 and also PO4. Exercise. Yeah, give it a try. They are not difficult. All right, so far we only talk about the naming convention for these 2 proof obligation. But how do we write them out exactly as sequent? We kind of did it last time. Let me remind you. What we did last time was basically right, except that we try to combine these two invariant conditions together. That's not appropriate. But for what we did for last time, that was okay. But now we want to be 100% precise. What you need to put over here is just one single invariant condition. Okay? So let me just go back. Let's now do the one for this for ML out. Okay? So let's now take a look. And for this one, I'm running out of space. Why don't I try the new page? So you wouldn't get too messy. Okay, let's try that. The first one we want to do is ML out invariant 0, 1, and then invariant condition. The second one will be also for ML out. But that one there will be for invariant 0, 2, and also for invariant preservation. What we need to have will be two sequence over here. Okay. Yeah, you might find it convenient when we actually do the proof later to actually box the sequence. It's just easier for you to see the process. All right. Let's now follow this rule here faithfully. Okay. Let's try. Let's start with the axiom. The axiom will be over here, which will be the natural number. Also the natural number. Also invariants in the pre-states and all the invariants. So all these. Okay, so n natural number n less than or equal to d. So n natural number n less than or equal to d. All right? And then the next one, the guard of the events. Since we are talking about ML out, so whatever guard it is, it should be put. But in this case, it's true. All right? So let's put true over here. Let's put true over here. And of course, we've still got a sequence over here. Right? So far, you can see the antecedents over here are all the same. That's okay, because we're talking about the same events. But if you're talking about different events, their guards in general could be different. Okay? What about this part over here? So this part, I do have some recommendation for you. From what I observed from my students from last year who took the same course, this part here confused them about how they're supposed to put it. I would suggest you try to do some intermediate step to help yourself to see how you can derive the final form. First of all, try to copy down the invariants from the corresponding invariant to here first. So here we talk about invariance 0, 1. Okay? So the first one to do will be invariance 0, 1, which is over here. And a natural number, first of all. But we are talking about it should take the effects of the events. So that means it should be an invariant in the post states. So I would say prime first. That's step number 1. Whatever invariant condition you have, copy that and then prime all the variables to denote that it's actually the post-state evaluation for the invariance. All right, that's step number 1. And then from there, you're going to consider the effects of the events. In this case, it would be the effects of ML out, which is m plus 1. Right? That's what we talked about before. So I can now replace every occurrence of m prime by n plus 1. You can see there's no prime in the final form. But as an intermediate state, you can put prime. Might just be easier. If you're very confident, feel free to write down the final form directly. So this will be the first sequence that we have to prove related to invariant preservation for this particular invariance and for this particular events. Right? What about this guy here? This guy here has to do with invariance 0, 2. Let's do that. invariant 02 is over here. Okay, and first step, copy that down. N less than or equal to D. And it's supposed to take the effect, so it should be prime. And then I'm going to replace this n prime here by the effects, which will be n plus 1. And you don't need to simplify that any further. That's good enough. All right? All right, guys, are we okay about working out the exact sequence? Of course, we haven't really proved that sequence yet. So here, what we are saying is, I'll take a question in a moment. This sequence here can either be true or false. It would be true if you can show that this is provable, assuming this. Also, for this sequence over here, it can be true or it can be false. To prove that it is true, you have to show that this is provable, assuming this. All right? And to really prove it, we need something called inference rule to really do the proof. You got some question, right? Go ahead. The true, yes. You mean are you talking about the true over here? Yes, okay. So in general, you have to make sure the guard of the events, meaning that we can only, okay, thinking this way. I'm glad you asked. Let me try to explain a little bit more. Think about this guy here and this guy over here. They are related, okay? Effect of an event only occurs if the event is enabled. So if you didn't have this, that's not right. Because how can the effect taken if you didn't assume the event was actually enabled? So think about this guarding condition here is to say I am assuming that the event is going to be enabled when I take effects. So that's why the guard should be here. But now for this event here, it's very special. It has no guard being specified. As we said before, implicitly, it will be just true. You can leave it there, that's okay. We're going to learn some very convenient inference rule. For any assumption which you want to ignore, you can just drop it. You don't need to worry for now. But I think having this explicit over here can show to you we are not ignoring this. You cannot. All right, guys, let me recap. Very important point. The reason that we got a G here and the E here is as follows. The E here tells us the effects of the event actually occurs. So we can do some substitution for the invariant in the post states. But conceptually, for the effects of the event to occur, its guard must be true. Otherwise, the event will be disabled. Then how can that effect occur? Right? So that's kind of logic over here. So both should be there. All right? All right, any question? So what will be the exercise for you guys? Similar, so it will be exercise over here. Formulates proof obligation 3 and proof obligation 4. And those are the part 1 exercises I assigned to you. So this is like a part 2. Right? In part 1, you want to figure out their names. Part 2, figure out what they should be. Okay? You will definitely find some answer in the slides, but I will encourage you to try first. Right? You will be asked to formulate sequence like this, for sure. Okay? Why don't we take a short break, and then we can talk about inference rule. I think now it's good to have a pause. Okay? If you guys can just get ready, and then I will start a poll. Bear with me. I'm going to start a class. And then start a poll. Let's say this one here. All right, check in, please. Yeah, if you got any trouble, please come forward. I got a sign-up sheet for you. Otherwise, come back in about 2 minutes. Okay? Everybody's good? No? Okay. That's okay. I can wait. No, sorry. Yeah. Guys, are you okay for the check-in? I can stop? All right, if you got any trouble, come forward. Otherwise, yeah, 2 minutes. Oh, got in trouble? Do you have a pen? You may want to maybe use a pen from your classmate. Yeah. I'm not sure if I have a pen, actually. I may. Yeah. Let me ask. Yeah, just ask. Yeah. Yeah. Good. Yeah, just find your name and then check and signature. It's sorted by last name.
Okay.
Thank you. All right, 1 more minute, and then we'll resume. Oh, sorry. Forgot about that. Yeah. All right, we'll resume in just 1 moment, please. Just 1 moment. All right, let's get started again, please. Okay. So before the break, we learned about how you can formulate sequence like this. And as we know, sequence itself tells you there is certain implication hypothesis implies the goal. But we don't necessarily know whether or not it's really true. You got to prove it. Okay? How do we prove it? We have to make use of something called inference rule. Let's talk about it. Okay? If I go back here, inference rule. What will be the syntax and the semantics? So syntax of the inference rule is not exactly the same as the sequence, but it's very similar. Okay? So this is how an inference rule looks like. Over here is just a horizontal bar, like a line. Sometimes it can be very long if the inference rule itself is complicated, but it's not turnstile, by the way. Okay? And what we want to do is to explain about the syntax and its meaning, and then I want to clarify very quickly about how you can distinguish between what a sequence really means and what an inference rule really means before we do some example. That'll be the plan. Okay? So for inference rule, we got, okay, so let me just go directly to the notes. Okay, we can talk about it. All right? Let's start with this. This one here is called antecedents. Okay, it will be an antecedents. Antecedents. And this one here is the consequent. And it's very important to note, for our context for this course, both antecedents and consequence, they are sequence. All right? Let me write it down first, and then we'll see example very soon. Antecedent here is a set of sequence. And consequent here is a single sequent. Right? And do you remember that what formally is a sequent? It's basically an implication. So we basically got a bunch of implications here as the antecedents. And we got a single implication over here as a consequence. And somehow I can tell the horizontal line here also means implication. So we basically got just another big predicate which has lots of implication. That's the big picture. All right, let's now talk about the semantics. If you have A horizontal bar and C, that means the following. That means A implies C is true. It's more like this is always the case. It's an axiom. That's what we're saying. Let's now do a comparison right away between inference rule and also sequent. Okay? So if you think about sequent, okay, versus inference rule. For sequent, you would say hypothesis, turnstile, the goal, right? That's what you would say. And formally, H implies G. And this here, provable or not, we don't know in general. You had to prove it. For inference rule, it's already provable. It's given to you, so you can apply it. For inference rule, you're going to get some antecedents and some consequence. And then this one here will just be A implies C is equivalent to true. Okay? And let's dive a little bit deeper into this. Okay? There is an informal meaning, which I'll try to explain to you a little bit. How can you okay, let's now switch the context back to this guy over here. Okay? How do we interpret that? On the slides, you will see over here. So formally, A implies C equivalent to true, so that's an axiom. Informally, this is important. Okay? In order to prove C, it would be sufficient to prove A instead. What does that mean? So here, we are saying that the implication itself is true. If I want to prove that C is true, what should I do? What's the only way to make something implies true to be equivalent to true? When this is true. Okay, that's how I understand it. Then this must be true. Thinking this step. Step number one, the implication should be an axiom. And to really prove C over here, you must show that the antecedent over here is true. Okay, just some principle over here. We'll see example. Don't worry, we'll see. Okay, let me see if I missed anything here. Okay, let's now try something over here very quickly, and then we'll see example. What does it really mean when the antecedent over here is simply missing? So, Ryan. Yeah, consequence is always true, absolutely. Let's now take a look. So if I have A, I don't have A anymore, just C. Okay? So that now by definition is simply going to be formally true implies C. It would be as if the true is already there, right? Okay, and then this tells you C itself is simply equivalent to true. So this means the consequence is itself an axiom. We'll see some example like this. Itself is an axiom. All right, let's see some inference rule. Okay, I'm going to talk about two of them, which are very useful. Okay, the first one. Okay. Oh, by the way, just one thing. Sorry, I forgot to mention. We got some L over here, so usually just a label, like a name. Name of the inference rule, and we're going to see about close to 20 inference rules for this course. That should be enough for you to do any proof that's going to appear on the assessment. But we'll get them there. We'll get to them as we go. Let's look at inference rule number 1. Just to get some idea. Okay, let's look at one example. That should be enough. So this is how it looks like. Okay, so now we got H1, H2, G. And then we say H1 over here, G. Okay, let's see here. And let's try to see how we can interpret this. This is to say, if I have a sequence with 2 hypotheses, it would be sufficient for me to prove the same goal given just a single hypothesis. What does that mean? That means I can drop hypotheses. All right, let me write it down here. Okay, this is actually, by the way, this will be always the first step you have to do in your proof. Okay, but let me write it down here. To prove H1, H2. It's sufficient to prove by dropping a hypothesis, which will be H1, G. Okay, let me recap very quickly for you guys. So here we're saying this. If I want to prove this one here, I can prove something that's simpler instead, where I simply drop H2. I only got H1 left. That's what I'm showing. Okay, I'll give you a concrete application of this rule right away. Okay, let's say this. Let me just copy this. Okay, let me give you one example here. It will be very important for you to see how this can be applied. All right, that's the inference rule. Okay, I'm going to copy one of the proof sequence, one of the proof obligation we had earlier. Okay, let's take a look. Okay, doesn't matter which one we choose. What about we choose this one here? Let's be very clear about what we're doing here. This is some inference rule you can use to apply whenever applicable. This is something to begin with, is a proof obligation that we would like to show provable. Okay? And when I say it's almost always the first step that you have to do. So what do I mean? Okay? And this one here, I can fix that a little bit. If you remember from before, this should be n plus 1. Okay? Okay, like here. Let's now be very careful about the correspondence. Okay, so let me try to use maybe better color just to show to you. Okay, let's say this. Can you find this guy here in the rule? Where is it? In the inference rule. If I want to apply the rule on this particular sequence, that means somehow this sequence here can match somewhere here. Anybody? Go ahead. Yes, please. Okay, how about this? I'll make it easier for you to refer to it. Let's say this is the antecedents and this is a consequence, right? Do you think this guy here should really be matched to this, or both, or neither? That's basically the question. When you say both, that's not good. No.
I think actually, no, I think the entire rule should be a consequence.
It cannot be both. First of all, because there's a horizontal bar over here. So you can, this is, first of all, this is a sequence. You can either match this or you can match this,
Yeah.
right?
The entire rule should be what are the consequences.
It should be consequence, and let's now talk about why it's not a good idea to really match this to this. Because we want to prove this guy here to begin with. In order to prove this, we want something that's simpler to prove instead. So that's exactly the spirits of this particular inference rule. Let's remind ourselves. To prove C, which is over here, it's sufficient to prove A, right? So now, in order for me to prove this, it's almost like I'm saying if this is the consequent. In order to prove the consequence, I can prove something simpler. That should be the flow. If you say that this is matching this, then it's not right. You never start with the antecedents. All right, guys, you can see what I'm doing here? I'm trying to solve some very deep confusion here that might occur. Because later on, you might just get very lost. I got some sequence here. I got so many inference rules. What am I supposed to do? You want to think about this is what you want to prove to start with. You should always try to match the sequence you want to prove, which might be the beginning or somewhere in the intermediate sequence. Match that to some consequent of some inference rule that tells you in order to prove something complicated, how you can prove something that's simpler. Right? That's a very important insight into this. I'm telling you right away. And let's go a little bit deeper. How can we match the pattern of this guy here into this? Right? Ryan.
If each one is true, and the rest, like D belongs to N and belongs to
Actually, we are not trying to prove anything just yet. We're trying to match some pattern over here. Let me just go, maybe give you guys a little bit of guidance over here. So this guy here is the goal, right? And this part over here can somehow be broken down into H1 and H2. H1 itself can be a set of predicates. H2 can also be a set of predicates. Depends on how you want to break it. All right? So one way to break it would be, for example, we can say, let's say H1 could be, let's say, this one here. And H2 that we're going to drop can be just the rest. The order doesn't really matter, right? Because the afterward, in the assumptions over here, it's more like a this and this and this and this. And the order of the conjunction doesn't really matter, okay? So what we're trying to do is H2 really correspond to this and this together. H1 really correspond to this. So now, how can we apply the inference rule? Okay. So this inference rule has its name. Okay, I'll give you the name right away. It's called monotonicity rule. Monotonicity. Okay, basically you can drop hypothesis as you wish. And how do we write this? We can say by applying the monotonicity rule, we can get another sequence. And that sequence over there should really match the antecedent over here, right? What should that be? Only H1 should be left. The other H2 should be dropped. So what we got is we're going to get n, natural number, and then n plus 1, n. So you can see this one's still here, and this one's still here, right? This one's still here, and this one's still here, right? Make sure you really understand what's really going on. We have some sequence to prove, and somehow we can simplify that into another sequence to prove instead. This step over here should be justified by a single inference rule. That's really important to really get, okay? That will be something you have to do many times in the course. Okay? That's why it's really important to clarify that. And you might be wondering, what about this guy here? This guy here, there will be another inference rule, which says that if you got this sequence over here, it's going to be proved automatically. Okay? That's something we'll see. Okay? So this one here, I forgot the exact, let me see. There will be another, let me give you the name. Okay? Just for your information, that one there is going to be something called P2. That's something you will see later. I'll go over the inference rule just for this week, so you will know. And what's really P2? By definition, P2 tells you the following. It is an inference rule that has no antecedents. It tells you this. If you got n natural number, that means n plus 1 is a natural number. Right? Makes sense, right? Yep. And no antecedent. That means this one here is provable by itself without any further assumption. Okay? Okay, this is just another inference rule. It's called P2. Piano natural theorem, natural axiom about natural number. And that's it. So this, by the way, guys, this is a complete proof of sequent. We start with this, transform it into something by dropping all the irrelevant hypotheses. And this sequence itself matches the consequent of some inference rule, where the antecedent is empty. That means we don't need to prove anything further. Okay? Nothing to prove for the consequent. It is automatically an axiom. Okay? All right, guys, any question so far? Please. I'll go with you first. No, here you can see, and so this is P2, right? This is an axiom inference rule that we will be given. So here you can see this one here matches this one. This one here matches this one.
Yes, this one, if you assume this one is P1.
P1? What do you mean P1?
Just like just give a name, because I don't know the name of this.
So what's your question? Go ahead.
How can we justify if we prove how can justify if we prove the P2 then we get
No, you're not getting it. So we have this sequence as a proof obligation, right? We want to prove that this is actually true. In order to prove it true, we try to simplify its antecedents. So we get to some simpler sequence to prove instead. And that simpler sequence is automatically provable because of another axiom inference rule.
How can we get the simpler one?
By this rule. That's exactly what I was trying to talk about in the last 10 minutes, right? Okay. So go from here to here. You can see the only difference is we drop these hypotheses, right? The reason that we can drop them is because according to this inference rule, if you want to prove a pattern like this, you can simply drop some of the hypotheses and get something simpler.
So this is a rule, so we can use this rule.
That's exactly the point. So this rule is something you can use. And I would say typically it will be the very first step you have to. Because usually you will get many assumptions over here. Not necessarily all of them are relevant to your proof process. You got to choose which ones you want to keep. And you might ask me, so what would be the general rule for keeping what hypotheses? I would say it's hard to decide. You got to see. You got to try. Sometimes maybe you drop too many hypotheses, so you got to go back to maybe add more. Sometimes you might drop too few. So you still find that some hypotheses are simply useless. So you can drop more in the beginning. Ryan. Not really. Not really. because usually there might be another inference rule, but the way to read the inference rule is like this. In order to prove this, that's what you want to prove currently. You can prove something like this instead. Not necessarily, this below guy here is always more complicated than the above guy. We'll see some other inference rule, which will show to you sometimes you may have to add more sequence for proving. So that's something we'll see later. Always go from below to above. Yes. Question? Yep. Yeah, basically when you got H1 here and H2 over here, think about they're talking about two sets of different hypotheses over here. So somehow you can group your original hypothesis into two sets. And of course, since I want to get this one ultimately, so this one here must be the H1 I want to keep. And the remaining part together will be the H2, which I can drop.
So we only choose the only case it's checking for.
Yeah, because I kind of know, when I look at this, I kind of imagine that later on I want to use this axiom to actually prove the whole thing. I can find that this guy here is one of the assumptions. I only want to keep that one. In some cases, you may want to keep more than one in your assumptions. It depends.
So you decide what to keep based on the effect you have or the effect.
You kind of keep the ones you think that might be useful for later.
Okay.
Yeah. Okay, very good. All right, guys, I hope you're okay. All right, that's about everything you should really make sure you clarify yourself or clarify with me about how to understand inference rule versus sequent. Okay, we've got about 13 minutes, which is good. Let's see how much we can do. And now, what I just showed to you is really about how you can prove using the inference rule in general. So this will be the principle. It's more like an iterative process. So you start with some outstanding sequence for which you want to prove that's actually true. So you actually have to somehow apply inference rule, keep doing it until you got no inference rule that you can apply. For example, here you can see once I get to this part over here, I know that this one here simply corresponds to P2. And this is an inference rule where we have no further things to prove. That's when you know you can end. There are other cases where you might end up in a sequence for which you have no inference rule to apply, in which case you cannot complete a proof. That one there most likely is because maybe your model itself is not good enough, so you have to fix it. That's something we'll see. We still have some time to see some examples for today. Okay? Yeah, if this structure here is really bothering you, I'm sorry. That's something you have to work with for the rest of the course. Right? Whenever we do any proof, this will be the kind of formats we have to follow. Okay, so the formal proof, that's something we just did, right? We just did it on the page. Okay. And let's now talk about different inference rule. Okay. Let's now take a look. Give me a moment. Let me see what I can. Okay, let me see. Okay. This will be the first inference rule. It's called P1. So it's the piano axiom. Okay. So 0 is a natural number. Whenever you see a sequence where the consequence, whenever you see a sequence where the goal is 0 is a natural number, it's just proved. All right. And P2. I'll make some PDF available to you as well, so you can also print it as a reference. Okay? And for P2 over here, you say that if I have a sequence where the goal is n plus 1 is a natural number, all I need will be the assumption that n is a natural number. All right? So if I got a sequence like this, I don't need to prove anything further. It's automatically proved. Right? You can see the very important characteristic of the so-called axiom inference rule that tells you once you get to the case where this bottom part can be matched, there's no further cases for you to prove anymore. So that's more like a base case. It was the other flavor as well. And the third one here, well, like a variance to the second one. If I got n is positive, right, assuming that n is positive larger than 0, then n minus 1 should be natural number. Intuitively, what will be the largest positive, what will be the smallest positive number? 1. 1 minus 1 will still be a natural number, right? And any larger positive number will still give you a natural number if you decrease it. And the final one, if I got n, assuming that n is a natural number, that means n should be larger than or equal to 0. So these are very simple rules, but these are very important base cases to terminate your proof. If you can somehow get to this level here, that means you're done. Okay? Other inference rule will be something like this. This one here, let's take a look. I'll try to help you a bit in interpreting this. We got increments, also we got decrement, right? Oh, over here. So let's take a look. Increments and also decrements. So increment here, let's say if n, think about number line, m here, and n here. N is strictly less than n. If I say n plus 1, the most you can get to will be just the same position as n. You cannot go over that, right? Easy to interpret. Okay? Similarly, like this. If I got this, let's say, so n should be smaller than or equal to n. So n can be either the same as m or n can be over here. If you say n minus 1, you try to move to the left, you're definitely still to the left from m, right? So these are also rules you can use. And so 1, 2, 3, 4, 5, 6. So these are all the axioms you can use. If you can really find some sequence matching the consequent over here, it's automatically proved. But it may not be that lucky all the time. So that's why we need some other rules over here. So these are the terminating cases, the green ones. Terminating rules. And all the red ones are not terminating. Non-terminating. That means you may have to do more. Okay, let's try to interpret them. And let me get to this one a little bit later, because I do have some nice proof to show to you. Maybe not in class, I do have some nice illustration. I'll include a link for you. But I can give you some highlights about what you should really watch out for. Let's try to interpret this. Guys, anyone want to try? When you look at this rule, what does it really mean? Just this one. Ryan, give it a try. Yes, what does it really mean when you look at this?
I'm interpreting it like truth value, so age implies P or Q.
Sure.
If P is true or Q is true, then
Yeah.
it just means that the whole.
Yeah. Okay, I can try to maybe formulate what you said, but I would say that one is not too intuitive. Okay, I'll do both. This one here is telling you if I got H implies P, that implies H implies P or Q. Right? Basically, this guy here implies this guy. That's what we meant formally. But that's not intuitive enough. What does that mean? If I have some goal over here to prove, and the goal itself is a disjunction, then it doesn't really matter which goal I prove. I can either try to prove the left goal, or I can try to prove the right goal. That's intuitively what it means. So if you look at the name over here, R1 and R2, and in your assessment, in the written test or in the exam, applying this rule versus applying this rule, it makes a difference. Okay? This one is to say, if I got a disjunction over here, what I want to keep to prove instead will be P over here versus the Q over here, either the left or the right. Okay? Think about this one here. Oh, another thing to really show to you. What's the naming convention for the rule? The or over here is about disjunction, because you can see there's a disjunction over here. And then what about the R over here? That could be very confusing. The R here is telling you, where does this disjunction appear? Does it appear to the right of the sequence over here, the turnstile over here, well, does it appear to the left of the turnstile? In this case, it does appear to the right of the turnstile. We will see something like L later, okay? So this means to the right of the turnstile. Let me say that again. So this go over here is a disjunction. So that's why you got or over here. And this disjunction appear to the right of the sequence. So that's why you got R over here. And in this case, we can either choose to prove the left disjunct, that will be 1. Or we can prove the right disjunct, which will be 2. That's the naming convention, all right? Systematic, you just got to pay attention to the detail. All right, this guy, we have seen that already, right? In order to prove this one here with so many hypotheses, we can drop some of them and only use some of them. All right? What about this guy here? All right, this is something we can understand, at least the naming convention. We talk about some disjunction, and that one appears to the left of the sequence, right? If you look at that one there, that means to the left of the turnstile, okay? This is a turnstile, and then the disjunction we have appears over here. Okay, that's how you interpret the name, okay? Now, what does this really mean intuitively? We're saying that in order to prove a sequence where one of the assumptions is a disjunction, in that case, I can split that into 2 sequences to prove instead. One sequence is going to use this hypothesis. Another sequence is going to use this hypothesis instead. Okay, so let me call it that. P here, Q here, and Q here. And this is only possible if that's a disjunction. All right? This is what you should really interpret that intuitively. Now, how do we prove this? Question first.
Yes. So when we get to the hypothesis, do we prove R, P implies R on itself, and P implies R by itself? We have like.
Yes. Yeah, so this is to say if I have a single sequence to prove, and that single sequence has some disjuncted hypothesis, to prove it, it would be sufficient to prove 2 sequences instead. And one sequence is using the left hypothesis. And this sequence here is using the right hypothesis. But it's really important to know that this should be a disjunction for the hypothesis. All right? Ryan.
The mathematical interpretation, why is it the...
So remember, yeah. So here, let me answer this quickly. And then, yeah, I'm running out of time. Let me answer this one first. If you recall what we did earlier, if this is inference rule, that means we are trying to show that this is actually true, right? That means this implies this is actually an axiom. Right? So what we are saying over here is, if I got this implies this, that should be an axiom. I didn't really say that. It should be an axiom. Right? That's why. All right, guys, one more thing. I want to talk about this one here. I'm not going to prove it. It's going to take some lines of code, but it's a very nice proof to actually get used to as well. Let's now try to say, if I really want you to justify why this is a valid inference rule, what should you prove to me? Okay. Think about this guy over here is the antecedents, and this guy over here is the consequent. Agree? What we really want to show, Ryan? Yeah. A implies C is actually a theorem, right? That's what we want to show. Very good. Okay? So let's now show to you very quickly what you have to prove. how do we put these two into predicates? This one here, we actually, for the convenience, let's drop the H. So we got less letters to write. So we only got this left. This one here, and also this one here. Okay, how do we justify that? The way to do that would be, so P implies R. This will be this sequence to prove. And also, Q implies R. This will be the second sequence to prove. If I can prove it, that will entail this guy here to be proved, where the assumption will be P or Q. And then turnstile will be implication and then R. So think about what's happening is like this. Sequent over here, sequence over here, and also sequence over here. We want to show that this itself is actually true, equivalent to true. That's what we want to justify. All right? And I'm going to include some demo video to show to you for you to follow the proof. Right? But I will encourage you to try to see if you can prove this. And this should be provable because this is a valid inference rule. Guys, I appreciate your preference. Just give me 1 minute. I want you guys to know what you should do during the reading week. Okay? So during the reading week, I'm going to give you some very about up to 1 hour lecture video to catch up with the missing time for Thursday's written test number 1. And then I think you guys will really have to make sure you follow through the lecture about sequence and also proof obligation and also how we talk about the inference rule for today. I think after the reading week, we still have to use them quite a lot. So I think reading week would be a very good time for you to study steadily for that. All right? And one more thing to tell you. So as I said in the beginning of the course, I'm going to give you guys a midterm course survey, completely anonymous, and then you guys can participate. And if we got certain response rate, guys can get some bonus. Okay? So that'll be something you can expect. I'll reach out to you sometime next week. All right, I'll see you on Thursday. Not here, Williams Small Center.